Yes, sir. We get that.
Prince? Okay. That's that, and then I just need to share my slides for our work today. Where are you? All right, here we go. Okay, so Bob, have you guys been practicing shear force and bending moment diagrams? Have you guys been practicing? You're all writing next week on this chapter. How are you guys finding it? Everyone's still asleep. Should be awake by now. All right, so the other announcement I want to make is that, in fact, this whole discussion, let's just quickly scroll to the test day. Where was that test date now? Yeah. I had to move test 2 to 1 o'clock because I have a subject review meeting with the faculty teaching and learning rep. So the main guy, so we'll be discussing this subject. So I had to move it from the morning session basically to the afternoon session. So that's for strengths. I think it'll be of benefit because it also give you time maybe to squeeze in some knowledge before that session. So just note that your new test will be, the new time will be from 1 to 3:30. Of course, this will be posted on Blackboard today. Now I got another question. I would like to make electros the Wednesday. I was thinking the Tuesday, but what do you think is the Wednesday okay for you guys? I know Mr. Kabaye, Dr. Kabaye is done with these lectures. A small discussion on that.
Yes, Wednesday is good.
Yeah, Wednesday afternoon, or should I have it morning?
I think anytime, so the longer, more often, the better.
Okay.
Maybe not like 9 o'clock in the morning.
Maybe 10 o'clock?
Okay.
Mr. Kiefer? Yeah.
Yeah, 10 o'clock.
That's not 9. Yeah.
It's not 9
See it?
that 1 hour makes it a lot easier for traveling.
Okay, fantastic then. Yeah, we'll see it.
Yeah, so you can also do it like afternoon, like it doesn't matter. So.
Yeah, I mean people want it. Okay, I think we can go for around 11 o'clock, right? I'll push for 11 till 12:30, somewhere there.
So,
Mr. Mataso? Yes.
yeah, I just want to know which Wednesday, this or the next one.
Excuse me?
I want to know
Next
which
Wednesday.
Wednesday. Huh?
Next Wednesday.
Next, okay.
Next.
Would be cool.
So,
yeah,
I pushed all your tests for next week Wednesday, so you're just gonna prepare for. Well, I know you have a low test now, but I want to give that day between. But electros, honestly, I'm seeing you tomorrow for it, and it's not that difficult. So, but you'll see how it goes. I hope you guys have been viewing the recordings for electros anyway. So, yeah. But we'll touch base tomorrow and iron out any creases for electros. But electros, yeah, shouldn't be a problem. I'm just concerned because I mean, you see, the thing is what I've come to realize is that the shear force and bending moment questions are very bulky questions. But I'll show you what the shear force and bending moments and thrusters are bulky questions, but thrusters is nice for a specific reason, and you'll get into that. So you can expect a spring question, a thrust question, and a bending moment question. I think the thrust question will be much more easier compared to the bending moment, and spring will be hard, but it'll be I don't think it's going to be hard at all, actually. It's going to be, if you studied your spring stuff, you should be okay. Okay, so that's just you got a new timetable. First thing to note, we communicate on Blackboard. I'll send that. I'll send it to the guys at from Sonatide or Manny Erasmus. I'll send it today as well. Good morning, Mr. Mzam. I'll send the test date for both tests so that you're aware what's coming in, and of course the scope for those as well. But electro is essentially all the work from term 2. But yeah, we'll get into electros in that period. So what I'd like to do today for the first part of the session is just continue shear force and bending moment diagram. So I'll probably do like one example.
Sorry, so just one question.
Yes, Annalisa.
Will we be off from the 31st?
Let me just quickly have a look from the 31st. So
Yeah.
your last test is basically my test on the 25th or the 26th on Wednesday, and after that we have the 27th, 28th. Yeah, basically you're all from the 27th essentially. Honestly, the 28th. Are you with me, Annalisa? You
So
all
that
from
means
the,
there'll be
you
no
all-
lectures anymore.
Yeah, it shouldn't be, yeah, because Mr. Kabaya is done. Dr. Kabaya is done. Am I correct? Did he mention that to you?
Yes, he's done.
Yeah, he told
Yeah.
me he's done. So that's all the MEK subjects. And then NAVOC, how far is he? Mr. Levita?
I don't know.
Is that the
And no
question?
clue, sir. No clue.
Okay, but nevertheless, yeah, by the 31st, you have a study week. So a lot of people aren't happy with the changes
So
I've
we
made.
will be
But,
done with your subjects as well.
by this week, you'll be done, basically, with lectures. All afterwards is just prep. The
Okay.
2 tests, and then,
Okay.
is it all clear? But I made sure you guys
Yeah.
had that study week. And, you know, the bit of, even though it's uncomfortable to a lot of people, but, you know, I think it's only fair for you guys to have enough time to prepare, regardless. So, and maybe a small concentration here and there, you know. But yeah, it's been a rough semester for me. Okay. So you'll be all from then, yeah. So so you've written all your other tests, just strengths and electrodes, and then that's basically all. And hopefully you get your marks in that week of the 31st. So hopefully I'll be done. Well, I should be done. But anyway, so let's get back to the formal lecture. We all should be orientated now as to what's expected of you. So please focus on your tests for next week. Just push for this week. You have a break after next week, Wednesday. Small break, you can relax, I guess. And then we have to be back on it. All right, let's continue shear force and bending moment items. Okay, so this is the example I wanted to do. So guys, a typical example, I mean, I'm writing examinations example. So how does this type of questions it's going to get is that you're just going to have a UDL or cantilever, I mean a simple supported beam or cantilever or the UDL with a lot of concentrated loads in the UDL. So I'm going to show you something very interesting. So obviously we're first going to solve this problem, and then I expect you guys to sit and practice. This can be a difficult section, but also an easy section. So and it's literally ask you the same stuff all the time. So please, these are big questions. So yeah, big mark questions. It's easy to score, easy to lose marks. Okay, so we can treat this session as like some kind of tutorial session for shear force and bending moment diagrams. So please, I'd like you guys to participate. And yeah, and if you have enough time, you can do one more. But if not, then we have to start on trusses. But I've given you enough examples to practice from. So So, and also you've got a decent YouTube channel to refer to. I wish it was my own, but hopefully in future I'll get to that. But anyway, first step, the first things first, we need to find the reactions, right? So I'm going to give everyone 3 minutes to find the reactions. Now remember, if you mess up the reactions, you essentially ruin the question. So you make sure you get your reactions right. Okay, so let's get that. So I'll give you 3 minutes to find that. So get your pens, books ready, and let's start solving. Might find another one in the meantime, but let's focus on this. Video. All right. Do we get it? Okay. So first thing is first. We treat our UDL as a point load. You can say 10 times 4. That'll be 40 kilonewton per meter. So that's 40 kilonewtons now. And then we can start with our first equilibrium conditions. So we know, assuming RA, RB is going up, all the vertical components anyway, and it's going to be 45 plus 40 plus 8 plus 5. So I'm saying something. No, 40.6 and 70.4. Let's see. We'll get to that now. Are you sure that's correct? You've already, that's a problem. It doesn't look correct. I'll tell you this. These guys up here, you should get 58 kilonewtons, right? Yep. So we can start, we can take moments on either side. So we can say moments at C maybe. So we're looking for the reaction forces. So we know the first force is going anti-clockwise, so it's -5 times 5 plus, you can say RB times 4, which is the force over here. So this is our, you could say it's called a load diagram essentially, but it's not really a big deal. RB, of course you have RC. Then we have our UDL, which at in the center is that's 2 meters away from C. That's going to be -40 times 2. That's an anti-clockwise moment. And of course at RC, that's 0. And then we have the 2 loads there, so that's going clockwise. So it's 8 times 2 plus 5, sorry, 8 times 1. And 8 times 1 and 5 times 2. That equals 0. All right. Oh, I see. Okay. So guys, make sure you get this right. It's very important. Okay, so we can just add up everything there. So we know R will be equal to 4. So I'm just going to carry over everything to the other side. That's going to be 25. In this example in your textbook as well. So 25 plus 80 minus 8 minus 10. So let's just quickly see what we get. $87. And of course, then divide it by 4. Then I'll get 21.75 kilonewtons. All right. Okay. Yeah, and then the other one will be 36.25. And if you use that, therefore RA is going to be 58 minus 21.75, which is going to be 36.25. Okay. Could we all do this? Oh, what's going on here? First important step. You get probably 2 marks here, 2 marks there, or 1 mark each, depending on the nature of the sum. Is everyone comfortable with this? It's very important. Okay, great. So next step, once we have that, now we can sketch our shear force and bending moment diagrams, right? So I think I'll just use white this time around. So you should just draw lines. You can draw your beam and then draw lines again at each. All right, I'll just have it over here, and that's 0. Okay. So how do we do it? So I'm just going step by step, just so that everyone, for the last time, so everyone gets a good feel for what's happening. Shear force at A. That's -5 kilonewtons. Shear force at B. It's going to be -5 plus RB, and RB is 21.75. That equals 16.75. We got a shear force at C will be -5, 21.75 plus we've got, of course, now
Sorry, sir.
yep, go for it.
So for the forces, for shear force at A, why is it 5 and not 0?
It's -5. There's a force at, look at A. There's -5 going down.
Yeah, I thought maybe this is for a different step, but I thought in the previous ones we used in previous questions it was all the forces to the left of A, which is 0 in this case, and then at B you would take into account A.
Yeah, so thing is we started 0, right? Going down at 5 here. And then we're moving on like this, and then that pushes that up. That's the idea.
No, I mean
Okay.
like at when you're determining shear forces at A, and
Oh, so
maybe I'm
forces.
misremembering.
Yeah, we're taking all the forces to the left. Yeah. So as you're moving across, as you're moving right, you're considering all the forces to the left, basically. Yeah. So if you look at, just do that again. Oh, all that. So if you look at A, right, you get all the forces at A, right? So that's going to be -5. So the beam is
Okay.
experience a shear force of, right, cool. And then you look at B, right? Then there's, with some of those forces, then it's -5 plus that. And then we go to C, then you get all the forces to the left, and that's essentially all the forces to the left, including the point, which is going to be -5 plus 21.75 plus the, sorry, that's -40 in this case. That's -40. And then plus RC, and RC is going to be, what's RC again? I had RN, RC, so just call it RC, sorry. And RC is going to be now 36.25. So just look at me there. Okay.
Okay.
Cool.
Okay,
Cool.
thank
That's
you.
all basically. You go on D, do exactly the same, and consider all those forces on E. You know you're correct with the shear force. For instance, you're going to end up here on 5, and then that's, sorry, you're going to end up on 5 on top, and that's going to push it down to 0. That's when you know you're correct, because the beam should be in equilibrium. Yeah.
Okay, thank
We
you.
have to be a bit careful when we actually do that. I'll show you now why I'm saying that. And then this is going to be equal to what's that? C 40 plus 36.25.
13. Let's see.
That doesn't look right. Oh, it's -40 there, sorry. Yeah, 13, that's 13. Okay, and then at D, I think at D we just have to subtract 8. No, we're subtracting 8. We have 5 left. That's correct. You don't have to do this part because it says you can mark the diagram, but it's good if you just do it. And then shear force at E will be 0. So sketching that. So at A, we're getting -5, right? That stays constant. Then we've been pushed up at B to 16.75. So I'm going up. So that's 5. So you can add 5 there. I'm aware it's below the negative, it's below 0, so it's a negative line. So that's going to be 16.75. And because of a UDL, we've got a triangle-like shape. Does that. So it goes to 16.75, and then it gets pushed up. It gets pushed up by that reaction, which is 36.25, right? And then minus 16.75 plus 36.25, which goes up to, so we get 13 there, right? There's a 13 there. Why am I? Yeah, it goes up to, let me just get this right. That's,
-23.
yeah, it's -23. Sorry, it's not symmetrical.
Yeah, -23.
Yeah, so that goes down. Well, let me just get this line right. Sorry, just made a mistake here. So it's not symmetrical because we have an extra force pushing it downwards. So that goes like this. Yeah, I just made a mistake there. Yeah. So that is going to be that's all the forces going down. That is minus 23, what minus 23 mean? What is it? Minus 5 plus 21.75 minus 40
minus 23
minus
times
23. Yeah, 23.25. And then of course, then we get pushed up further, and then that's going to be 36.25, and then that's 13. That makes sense, and that goes up again to 13, somewhere around there. That remains fairly constant. It gets pushed down to 8, and then coming across again. That remains 8. No, so that becomes 5 here. It's 5. Go across and then push 5 down, and that's your shear force diagram. Right? From a shear force diagram, where the shear force is 0, over here, you're expecting maximum and minimum bending moments. That's quite interesting. Okay. So you're gonna love today's lecture. It's all gonna make sense now. It's all gonna make sense. Okay. Is everyone happy with this diagram? You have to practice. There's no other ways to get used to it. It's not difficult, but it's just got to get used to the method. Is there any questions, students? I get a few thumbs up before I proceed. Any questions? Mr. Mzam.
Good morning, sir.
Morning.
Then if, like, for example, I take any direction here, the diagram is going to be the same, right?
So when you say any direction, what do you mean?
Like I mean, if I take clockwise negative and then I take anti-clockwise positive, the diagram is going to be the same, right?
Is that referring to the bending moment, or I mean, are you talking about the reactions or the shear force in bending? Because I mean, the shear force is very specific, you know. Grandson.
Okay, I'm talking about when I take the moments
Moments.
about, let's say, for example, I take moments about B, and then I take the directions for the clockwise is positive and then the anti-clockwise is
Yeah, it should be the same.
and
Yeah,
when I draw
think
this thing, it should be the same. Okay. Okay.
Yeah, because
So
the
there's no
reaction was
safety
told.
directions when you're drawing this.
Well, there is. I mean, the thing is, if you look at this beam, what this diagram is actually representing, just the shear force counterpart. You know, I think it was Mr. Matasio posted that video that. Yeah, assuming, let's say, I don't know if you guys all saw that video on the wedding, which I think you did, but it was you, right? And there were people getting on that beam across that, and there's obviously water here. There was water here, I think. There was water over here. And these are the people on the beam, right? So what happens is, what I'm trying to tell you is that as you load the beam, of course, the beam has its own limitation. So it has its own shear stress value, and that's what I actually mean, not shear force. And it has its own shear stress value, and it has its own maximum shear UTS and maximum allowable. You know, like, so it's a 355 or whatever. This is maybe God knows what. So 1 to 5 megapascals. To load the beam, two things are happening. Beam's either going to shear, depending on the nature of the beam and the way it's configured, and then also it's going to bend, right? So as I discussed, how the beam can fail in different ways. So what this is telling you is that as this beam is loaded as is, right? For instance, yeah, as is, the maximum shear force we're going to experience is 23.25, and assuming that this is exceeding, this induces a shear stress greater than the material can handle, it will break at this point. Are we all there? Are we all together there? So let's assume this 23.25 kilonewtons exceeds the allowable shear stress or whatever. The beam of fracture around this place here. Are we all, is it all clear to everyone of what this represents? That's where the maximum shear force is. So in the case of our wedding, as a loading the beam up, of course, the shear force diagram and bending moment diagrams were changing the whole time. It was changing because, I mean, of course, as you apply more loads, and eventually it exceeded the allowable stress within the beam. So yeah, I mean, I don't know, I'm not going off on a tangent here, but that's the idea of what you must.
Yeah, I just found out what I was trying to ask.
Yeah.
I just
So,
want
but your action is supposed to be upwards here. It can't be any other way because it wouldn't make sense for the actions to be down. The beam has to be balanced by the two supports. Yeah.
Oh, okay.
But you can take moments either way. What I'm saying is your values must be positive for the reactions. It can't be negative. That's impossible. That's the only thing I mean. You can take different directions, but yeah. Because otherwise, how's the beam standing still?
Yeah, but my action here is negative, sir. Like if I take anti-clockwise positive and then clockwise negative.
That's what I'm saying. It cannot be negative.
Yeah.
It can't be. It's a thing.
Okay, I get what you're saying.
Yeah. We'll see where. With the hand up.
Okay, thank you.
Yes, what is our reaction force at D? Like
At D, there's no reaction force at D. You mean C?
At D, like
D has no reaction force. Are we not? See, anyway, you guys are losing yourself there. There's two reactions. You know what the reaction is, right?
No, I'm talking about the shear force, the shear force. Like.
Oh, shear force at D is 5. Remember, it's 13 constant, and then it gets pushed down by 8, and then it stays 5, and then goes to 0 again. Why are you being what are you missing? So think about it. We have 13 here, positive 13, and then you have negative 8 going down, and then we reach 5, and then we stay 5. It stays constant here, and then we get pushed down to 5. I'm not sure if you get that. Okay, so let's find the moments now at our various sections, right? That's the next part. So I think we can do that over here somewhere. Taking moments at A, the sum of moments at A. I would say moments at A. It's always going to be 0 at the start. Essentially, there's no bending happening there. Moments at B. So we look at B. We'll only have -5. What is it? -5 there, and -5 times 1 kilonewton meter. Look at C. C is going to be -5 times 5, or B is 21.75 times 4, and we're looking at 40 times 2. I think that's what that should give me. Okay, so what do we get there? So moments at D. Moments at E. 0 as well. So can we all get that? You guys get -18 as well?
Yes, I got -18.
Okay.
But I did a different way. Like I came like.
That's fine. Don't worry.
From left. Yeah. All right.
I know the other way. Don't worry.
Yeah.
As long as you get the right answer. I just like doing it with the actual forces. It's perfectly fine.
All right.
Yeah. As long as you get the right answer. It's -5 times.
Yeah. It's -5.
So -5 times, what is this? 6 now? Plus 21.75 times 5. Yeah, let's add D. -40 times 3. And that's basically all. And you should get I think -5 here.
-5. Yeah.
Kilonewton. Yeah, and if we do the same, and if you basically add up all the moments on the one end, you're going to get 0. It's not always the case, but let's just confirm that just to show everybody it's true. So I said you always do all the principal points minus times what's it 7. It's 6. Yeah, that's 7 meters. Just to prove to everyone it's true. Make sure this. I'll give you time to just make sure you go over this. So that's 6 times 4. We're looking at is at RC. Oh, but no, did we miss something yet? Oh, we got it 27.5 plus 21.75 times. Oh, this is not right here. This is not right here. So we have 21.75 minus the 40 times 3. Yes, and then of course we have 36.25 times 1. That should give you -5. Yep. Check that out. And then 21.75 times 6. Is it correct? No. I already have 21.75. So this is wrong. This is 36 times. This is at ERA, so it's times 2. Yeah. And then -8 times 1. That should be 0. Students, do you know what I'm doing here? It's very important if you understand. Please ask questions. Very, very important.
So you just you said this is not always the case where the bending moment at E will be 0, or the bending moment at the end of the diagram will be 0.
Yeah, because it's an overhang beam, man. That's why. Imagine.
Okay, so if it was a different type of beam, like a beam like between two poles, it would be different.
Yeah. So in this case, it's just nice and 0. But if you have an overhang beam, sometimes you might find that, for instance, let's just argument's sake, I think. So just like building this beam up. So Mr. Rowe, imagine you had a beam. It's exactly the same, like that. And if I apply a load here, the only load I apply here, obviously, right? This beam is going to start. It's going to do this, right? It's going to bend that way. So as I'm saying, your maximum bending moment will be around there. But in this case, the reason why it's working out so nicely was they're applying a load here, and then we kind of balance the load with this UDL, and we balance the load with this, with that 5 kilonewton. So we don't get. But what I'm saying is, if you can, this is an overhang beam, and an overhang beam sometimes bending moment can actually be. You can have a big bending moment at the end of it, but in this case, it balances out by the other loads on the other end. That's what I essentially mean. So it's worthwhile just checking if it balances to 0, and also you know if you're correct if it's 0. It should close up, but I mean, yeah, sometimes it doesn't. But anyway, okay, so let's just plot that. So just remembering our shapes, we're spitting a parabolic shape here, which is a normal straight line. So this goes down to -5 over. Okay, let me just use green. That's -5 over there, right? And then we're going up, and we're going up to. That's negative. Is it positive? Where am I here? Is this bending moment correct here? Have a look here.
So it's
So
missing
that's
our
A.
turning point.
Sorry?
Our turning point.
Oh, you mean a point of contraflictia? Is that what you mean?
No, turning point on the shear beam. We have this, the turning point.
-5. Turning points. You mean I'm not sure what you mean. Turning points.
Yeah, I mean those points that turn from 0 to positive and positive
Yeah,
to
the point
negative.
of the point of contraflictia.
Contraflictia is for the beam, for the bending moments. For the shear force, we have a turning points, not.
Oh, you mean the shear force is 0? Yeah, that is correct. Yeah, these points are the green ones on top.
Yeah, and this point
Okay.
here for 16 to minus 25, we draw a line down and the take moment there to be our turning point.
Yes, that
of
is correct.
the-
Yes. Yes. Yeah, I'm with you. I'm with you. I'm with you. You're right. You're right. You're right. Okay, now, so I'm just using our values here first. I'm just sketching. We're still going to find that dimensions. Don't worry. Like this. Just give me a second. Give me a second. You're right. You're right. So MB, and then I'm just trying to figure out something here. And then at C, we have minus 18. I'm trying to figure out why my diagram. Oh, okay, I see, I see. So now, when you're hitting a UDL, right, it goes up like this. Then at C, it goes down to negative 18. Yeah, cool, that's fine. So we don't know, we don't know what this is, remember? So that's just negative 18. I think it zooms up. Doing the diagrams also a bit of a mess, but anyway. So minus 18, and then we add D, and D is going to be minus 5. So it goes up again, and then is there a UDL there? No, it's just a straight line going up. It's not a curve. Just go back. It goes up, and another straight line again, going like that. So that's minus 5 over there. Okay. Are we all on the same page, right? So this is 0. That's A. That's B. Sorry, that's A. Sorry, where's A here? A. Oh man, what am I doing? A, yeah, it's A, B, C, D. Okay. Do we all get that? No man, D and E.
So how do you know it goes like that? Because I drew a negative parabola.
A negative parabola.
Yeah.
I'll tell you now why. I'll tell you now why. Yeah. So I'm getting to where Mr. Okay, so the reason why I know it goes like this, because remember it's a UDL, right? And where this parabolic shape essentially comes from is, if you take you just get the UDL, we just call it W, and then we say W times X, that'll be the distance it's acting upon, and then it's X times 2. So W is I didn't show you the general formulation, I'll probably show it to you guys. It's the UDL per meter squared times X, the distance the span is on. Anyway, you end up with WX squared over 2. So the idea is that moment itself, if you look at the X squared, it's a parabolic shape. Fine. Okay, that's just the shape. Now you're asking me, why is it, you said you drew it a negative. Now remember, if you look at the diagrams I've shown you before, if you know you have a UDL, you're always going to expect this up. It goes up and then goes down. I'll show you now. Where is it now? Just give me a second. Yeah. Okay, right? It always looks like that. It's always going to be this parabolic shape going up and then going down. That's always the case. It might not be symmetrical, but it's always going to go up and then going down. That's how you know. Okay, but now there is what we should do now is like what Mr. Mataso said. So now if we want to find the moments at those particular parts over here. So I might ask a question, what's a bending moment at the points where the shear force is 0, right? So we know that one is at B or round about B. No, it's not at B. It's just over B. Somewhere here actually. It's not actually lined up here. This is not actually right. And we want to find this moment, because thing is, we're assuming that this is the max, but we don't know as of yet. So we need to find what the peak is, right? I did this in the previous example. So can you explain to me how am I going to do that? So take our shear forces again at that particular point. Now what do we do? Tell me. Shear, I'm going to call it an X, right? Can I just call it X?
Is our X.
So we say, yeah.
Yeah,
so shear
sir.
force X. Go for it.
There is a simple way to find this turning point.
Yes, similar triangles.
No, this one, yeah, can be similar triangle, but I just do, the book says you do like from B.
Yes.
From B, you take the shear force at B.
Yes.
And divide by UDL. You get your point from the distance to B.
So 16.75 divide
by the UDL
10.
Yes, it's our distance.
So this is going to give us 6.75.
Yeah, from B.
But from B, right?
Yes, sir.
So, but the problem with this is that, like, why does it work? You know, it's not asking. You know, why does it work?
So I think that's 1.675.
Oh, sorry, my bad. Yeah, 1.675. Okay, so if you have a simple way, fine. But
yeah,
what I do is I'll show you shear force at. The reason why I show these long ways is because it gives you a way to figure out stuff. But anyway, it can be a bit confusing. So we just take the shear force at X. It's going to be 5. It's going to be RB. What's RB again? Plus RB is 21.75. And then, of course, we have the UDL thing, but we don't know how far the UDL acts. So it's going to be 10 times X over 2, right? I think. Because we don't know the distance over there. We make that equal to 0. And let's see what we get. That approach is using similar triangle. That's like you can take. That's what it actually is. So if you find a convenient way of doing it, please do it and let me know. Maybe I'll teach it better next semester. Wait, this is not why am I doing this? There's no need for that, sorry. This is not a moment. It's just always 10x. 10 times x. Excuse me, I thought that was a moment. Keep doing that. 10x. So we add this guy up, we should get minus 16.75 equals plus 10x. And equals 0, and just get him 16.75 equals 10x. So, Mr. Matas, do you see the same thing what I just did now? And you should get 1.675. Yeah, so I'm just showing you. That's just if you can do that, that's perfectly fine. I mean, but of course that is from B. 1.675 is my that is, where is that distance? No, that's at 1 point. Yeah, that's from, so that's going to be 1 plus, so 2.675 from A, from right hand or left hand support. Does it make sense? Around there somewhere. Yeah, that's 1, 2 point, yeah, you could say. Okay, so that's just the way that's the one thing, right? So then once we have this distance over here, we can check what that bending moment is now, right? And the bending moment here, we just have to take the bending moment again. I'll say bending moment at X. That's going to be exactly the same. So we're just going to say 5 times 2,675 675 and then it's going to be, we're just looking at an X point there. So we've got the reaction, the B reaction, which is plus 21.75 times 2,675. This way is clear. I hope some of them, I feel like I'm confusing you guys. It's just a very unnatural approach. That's the thing. And then of course this is the UDL. What is the UDL value again? It was -10 times 2,675. Remember, this is just a load, and then now we must divide by 2. I'm hoping you get the moment. You should get 8.5 here. Yeah.
This distance 2, is from A. B, I don't know if, I think you do in different way. B is only 1,5. I don't know.
Yeah, maybe you're right. I'm not sure. I'm just like looking back and forth. That's one. So you think it's 1.675 from A. I'll see now. You could be right. Yeah, you should be. At X is that point. I think it's. Just give me a second. Yeah, you could be right. 2.675. Just make sure of my stuff here. 2.1 is it 1.675? Yeah, that. Maybe it is. It should be from A. It's not from A. From B. Just get it right. We should get that. Oh, their value is 8.5 at that peak. Oh, but that's at 2 meters. That's exactly at 2 meters. Oh, I see. So we should get. It cannot be more than 8.5. So it's 2.675. Let's see. What do you guys get for that bending moment there, that X value? What I'm actually doing is a bit of an overkill here, honestly, students. What I'm picking up here. Yeah, I'm getting a. Can it be 9? It's possible. Yeah. Okay, I'm getting 9.02 positive 8. So this is a bit of an overkill here, right? I think what they actually did, but don't worry about it. So I think at that point, at 2.675 with the shear force 0, I don't think this is typically incorrect. But what they have, I think this is our point. This is arguably our point. So that is fine. But that was a more of an overkill now. Okay, anyway. That's just to find that piece here. Nevertheless, what they actually wanted was the position and magnitude of the maximum shear force in bending moment. So the maximum shear force is here, right? So V max. Oh, we don't have enough time here anyway. Okay. V max is equal to 23.25 kilonewtons. Is that C, I think, right? And Max is at where is that? Oh, it's -18 at C as well. It's basically the same. On the inside of the one, the right hand support, and yeah, it's just all vague. But I'll shape this. We'll do it now. I'll show you exactly. Okay. So students, not to be lost or anything. What we're just doing to find where this particular point is, right? So what they basically did, look at the textbook, they just found at 2. But what we did, we actually found where the maximum was. So we actually got 9,028. And you'll check this answer, don't worry. I'll show it to you now. Are we all on the same page now?
Yes, sir. I also got 9,0.
Yeah, it's fine. It's fine. You will enjoy what I have to show you after this, so don't worry. So we're all happy with the students. Please do not be lost here. So that was just to find that point. Okay, so now the next thing is to find the points of contraflictia. And again, points of contraflictia are where there is no bending moment or no bending stress. Remember this, might come up somewhere, right? It's when the bending moment changes from negative to positive. In this case, we have one over here and we have one over there, right? So it's very important to note. Right? So normally you might find 2 points of contraflictia, right? And the way you're going to do it is by taking moments at that particular point, just like we've done over here. So what I want to do is just get my Trotsky book out because I want to have a need. I'm actually going over my allocated time for this assignment anyway. I'm going to find that I need the diagram here. You're going to have to practice. Yeah, it does take some time to get used to it. I remember when I started learning this, I had a bit of a headache. But I have something to assist you to make it easy. You can verify your answers. All right, okay. So I'm just getting a nice actual diagram so it can look a bit neater. All right. Okay.
Sorry, so was
Yeah.
X,
Go for it.
was X 1.625 from A or from B?
Yeah, so obviously it has to be from B, right? It has to be there. And because if it's from A, whoa, it's a baby. What I'm feeling that it's actually from A. But things you're taking, so let's just talk about it, just to figure it out. Is we're taking the shear force at that point, right? So from where we're referencing this point, so normally when we're taking the shear force points, right? Even the previous examples. That we're always taking, if we're taking it here, I'm definitely sure we're adding the one. If you just take the previous examples, it's essentially the same thing. So it's from A, it's not from B. So we get that dimension, but then you have to add the one from the other end. Because we're just taking it from that particular point. Because remember the UDL is only acting, at that, at that particular point. But you'll see now, don't worry. It'll all come to light soon. So we're gonna do this, do the software I want to show you, and then we can take a break and start on trusses. So it's a really good sum to actually go through. So students, we're gonna end off with this point of contraflictia for this particular sum. So I said it's over here. So you listen to answer questions from A, right? And we'll see if it's true or not. So I'm just give it there for now. Okay. So we need to take moments from here. And there's another one over there, right? Cool. Okay, so I'm gonna call that moments at G, which they have. You can call it obviously any letter. And the aim is we find the points of contraflictia. This is where no bending stresses are in the beam, and this is normally where we want to join the beam, so that our joints do not suffer from additional stress. Okay, so the first force is -5 times, we can call whatever the distance we need to call that. We can call it X or Y, or we can call it Z. Zoom it in. We can call that Z. Okay, we've got that. I think that's correct. And then we have our What is this one? No. Let's get this right. Yeah, then we have plus 21.75, and that's going to be 1 minus Z, which is that small distance over here. That's 1 minus Z, I think. That should be 1 minus Z.
I think it's Z minus 1, sir.
Z minus 1. Yeah, Z minus 1. Thank you. Z minus 1. Thank you, Phil. Definitely Z minus 1. Z minus 1. Yep, that's correct. And then we have our UDL, which acts only on that small piece there, and that's going to be minus 10 times X. That's the load, and then times X over 2, make that equal to 0. And that's also not X, so it's going to be Z. Just forgive me for my bad habits. So that's it. Okay. Cool. Don't know why it's going to be all fun and games just now. So of course we have to simplify this out. If we do that, minus 5Z plus 21.75Z minus 21.75Z minus 10. Oh, sorry, we can just call it 5Z squared.
So can I ask, why are we using Z instead of X there? Or Z
No
instead
reason,
of Z
no
minus
reason.
1 there?
No reason, we could have used X.
No, sorry, no, I mean like, why X? Why are we using Z and not Z minus 1 there? Is the between the 5 kilonewton point there and G, that's where the UDL
Okay.
starts, is it not?
Are you talking about for the UDL?
Yeah, because the UDL
Yes.
is not the Z point there. It should not be Z minus 1.
No, sorry.
Where
That's
the
my
UDL
bad,
is.
my bad. You're right. It is 10 times Z minus 1. Sorry. It's because I'm thinking with other things, man. Yeah, sorry.
Yeah,
And
no
then,
worries. Thank you.
yeah, Z minus 1. Yeah, right, yeah. And then Z minus 1. It's because it's becoming messier this way. That's why. Over 2. Cool. Yeah. Because I've taken a long way around and I'm realizing, oh, flip, it's a big mess. But okay. Yeah. So that's definitely correct, yeah. That equals 0. That's correct, yeah. I should have still taken Z, 1 plus Z, and now I'm sitting with this mess, but anyway, it's fine. So minus 5Z plus 21, that minus 21.75Z, and so of course this will be minus 5Z minus 1, but thank you for that squared. All right, it's like a mess here. Oh, my bad. This is just 1. So let's add up all so it's minus, I'm just going to rearrange this in the right form. So it's minus Z minus 1 squared. And then we have to add up that minus plus 21.75, which is plus 16.75Z. And then minus 21.752. It's a positive, sorry. And that equals 0. Okay, so now obviously we have to expand this thing. We have to kind of expand this whole quadratic thing. The Elijah took a long way around, so I'm saying long way around. So you have to expand that, and you can solve it. You can even call this X and then work. Yeah, I'm not gonna go that way. function and get the roots of that equation. And you should get two roots. Normally one is not worthwhile. So one Z value is going to be 3,018 meters, and one is probably useless or not useless actually. And one is the other Z value is Z equals 0.3316. So you can just use a calculator for this, right? Or you can do your good old quadratic equation if you want to be all fancy and whatever. But of course, a calculator can do that. So once you get the one value, this is all relative. So this is the Z value we're getting. Remember, that's the actual value we're getting. So we have to add. We have to add 1 to both of them essentially. So 1 is going to be, it's basically the value over here. So this is 1.33, and then the other one from here, which is that's going to be 1 plus the 3,3018, and that's going to be 4,018. So that's that. And just going further from there till there. You're just lucky both values are positive. Sometimes the values are negative, and therefore you can't actually solve it. Okay, students, are there any questions? Did I lose you there? Yeah, this question took long, eh? Yeah, it's Shear was a Winbeam moment question after all. Are we all there? Guys, best time to ask questions. Let me prepare my. Any questions, students?
So I just want to know, say in that first
Go for it.
equation, which is
Yeah.
minus 5Z plus 21.75 in brackets 7 minus 1. I just want to know,
Yeah.
how do you get that Z minus 1 and how you get that Z? Like, I don't get
No, it's fine.
like how you
I'm
get
with
the
you.
distance. Yeah.
100%. Just give me a second. No worries. I got you. So over here, treat this whole distance like as Z, right? From here. Hey. Just give me, it's not removing itself. There we go. The whole distance with them as Z, right? Students, you got that as Z. So of course, that first piece there, grandson, that is 1. Is it not 1?
Yes,
That's
sir.
from A to B. It's 1, right?
Yes, sir.
That's 1. Does it make sense?
Yes, sir.
So of course, for us to get this, there must be Z minus 1 will give us that small piece. Z, if you want to find that small piece here, which we want, no?
Oh, okay.
Z minus 1, yeah. But like I said, it works better if you're just gonna go this way, like 1 plus Z. It's gonna be easier to get to the quadratic equation. Yeah, we can still do it, but then now we're gonna have to call this another thing. Now we're gonna say let Z minus 1, I don't know, be X, and you can try to solve it and then readjust the values. I'm sure we can do it that way, but that's mathematically, it's gonna give you a headache. Yeah.
So can
You
you
don't know
please
which
explain the term of the UDL?
Excuse me?
Can you please explain the term with the UDL, the 10?
10Z.
Yeah, is it
That one.
10Z or is it 10Z minus 1?
Oh, okay. So remember now, at this particular piece here, right? Annalisa, we don't know the distance. This X, that piece there, right? So, or 10Z, whatever, let's call it Z, fine. As we had. just going to sketch. I know you sound like I'm going over here, but I'm not actually. So the first part is, was it acting downwards is negative, right? We know it's acting downwards. Then we say 10 times Z, which is the force counterpart. Remember, it's force times distance, so this is the force. So it's 10 times Z. Normally say 10 times our distance. In this case, our distance is Z. No, a UDL X halfway between the distance. So Z divided by 2. You got it now. That's where it came from. That's why it's like that. Are you there? To get it? So 10 times Z is the distance, like 10 times 4, right? But then you still need to know the moment. In the moment, it's actually halfway between. Yeah. That's the idea there.
Yeah.
But with the shear force side, obviously the shear force, we don't do that because shear force, we're not looking at the moments here. So we're just taking the forces. So just 10 times X. So when you come to the bending moment diagram, you always going to have to times by distance, which is probably X over 2 or X, whatever, for UDL. Or Z in this case. Then students, can I carry on? I want us to go to half pass and then have a break and then get back for the last chapter of strength. Like I said, this is going to require a good amount of practice. But once you get it, you get it. So, and we only have 3 chapters to prepare for, but it's not 3 chapters only, it's a lot of work actually. Okay, is there any questions before I move on to the part where I actually want to show you something, the good part of the lecture? Can I move on? The people, you be quiet, eh?
Yeah, no, I'm here. Don't worry about me.
Okay, great. Good. So can I get okay, let me just go. So guys, I'll introduce you to software to aid you in your shear force in bending moment computations. Always gonna make you aware there's a software for everything in this day and age. But what's important is to understand how to use the software, and that is what's key. So it's a free software, obviously, and I want to share. I want to show you how I do the example on the software. And the reason why I'm showing you is that you're going to probably need it for Strength 3. And also, I want to show you so you can also check all your answers. You can check all your answers so whatever you work through, you can actually check it to see if the diagrams are all correct. You have to obviously sketch by hand. So let me quickly do that share now. Where is it? Share? And it's very easy to use. You just have to figure it out. You can always just ask me via what you call it. What is this thing called now? WhatsApp. So that's DSN Winbeam, right? I'll share the link with you. So what I'm going to do here, I'm going to sketch the beam in question and see if all our values are corresponding, right? So first thing we do, we go to normally to define your units, SI units and so forth, your beam element. So our length is a total of 7 meters. We choose elastic modulus. You can choose any one. In your case, your I section, you can choose an L section, select I. These values, you can select anything for this level. This is important for the deflection. We click OK. Next thing we do, we check the supports. There's a point load. So a point load, it's at the end of the beam, so that's at 0 meters at -5. I want to blow you guys' minds here. We have a pin support right at B, and that is at what? At 1 meter away. Beautiful. You see that? Can you see my shear force bending moment diagram? Are you guys all there? What's next? Got a UDL. So you go for uniform load, click on there. You guys are doing this. It starts at 1 and ends at 5, right? 1 meter ends at 5, I think. And then you can say -10. And the reason why I say minus to show it's the direction of it's going down or going up. Obviously, you can have a UDL going up as well. Wow, look at that. That's very interesting. Look at that shear force minimum. And then you can put the support at C, which is a roller support. Now, bear in mind, You can put your supports before or afterwards. It makes no difference. So that support is at 5, I think. There you go. That looks good. It's not starting to look familiar, Mr. Hermanus, Mr. Mataso.
It's looking familiar. It's looking good.
I wonder what's going through, guys. But oh, Mr. So is also here. Silas also mornings. And then what do we do now? We say point load again. That's it. What, 6 meters away from the end? -8. Hey, getting better. And then again, -5 at the end. So the 7 meter beam, -5. And what are we gonna get? Bam! Does it look familiar? Look at that value there. You see that 9,0281? Welcome. Welcome.
Yeah, that's what I get. 981. Yeah.
Welcome to Strength of Materials.
Beautiful.
Now, thank you, Chief. It really is beautiful. So now, any shelves and building my own diagram, you can check. Once, obviously, you have to do it by hand, but now you can check to see if you answer correct using the software. Mr. Doyle, where is my other champions here? Mr. Kabil, Robert, what do you guys think? Oh, Mr. Muche, what do you think about that? Quite. So, literally, I've shown you exactly, and what you can do now is you can take point on info, you can go on a point, and you can find exactly what that distance is, or roundabouts, so difficult to find the values. You can actually put it as a report here, but that's really important now. You can also say line info as you move across the line of the beam, you can roughly estimate. So what is the point of contraflictia again? What was it? 1.33. Yeah, man, my mouse is moving using my pad here, so that's around 1.33. Annalisa requested it's shear force. Can you see 2.67? Annalisa, do you see it? Around there, just forgive me for the sort of obviously. Yeah, there we go. And what you can also do is display rotation and display deflection. Do you know what the deflection curve tells you? Mr. Doyle, do you have any idea? Can you guys see it actually? Can you guys see the deflection curve?
I can see it, so I'm not sure what I'm looking at though.
That's the shape of that's the shape of how the beam will deflect. That's how it look like.
Oh, that's the shape of how the beam will actually look.
Up.
Oh, okay. I see.
Yes, like can you see it's very small millimeters, like 2.25 millimeters going upwards. I can't tell you the peak there. I can obviously check for you with the UDL is, and then it'll deflect a lot more at the end of 7.57991. You check there. At the end, man, the overhang will deflect around 7 moles for the setup. Do you guys notice, right, where look where the maximum bending moment is? You see there? Do you see where the max bending moments are? Is it the max bending moments? Anyway, so the software, DSN Winbeam, it is for free. Play around with it. Use it to check your stuff. Anyway, the deflection rotation part we do in Stance 3, depending on who's lecturing the subject. But anyway, nevertheless, yeah. So what do you guys think of this before I end of this part of the session?
It's very cool.
Think it's gonna help you?
So.
Yeah,
Cool
thank
program.
you. Thank you. Yeah, it is. It really helps. I think, and also provides better understanding. So you can actually see a few things. So what's cool is that you can actually solve all your problems, and then of course you have a fixed support with your cantilever. You can do a bolting beam if you want, and it works, man. You can actually see the diagrams, right? Let's hear some other opinions. Mr. Marat, what do you think about that? We're not going to say anything as usual. Grandson Zam, what do you think about it? Think it's going to help?
yeah, it's all good.
Great. Mr. Zuma. So guys, so my approach is that you attempt the shear force and bending moment diagrams by hand. Of course, you test it on that, and then you can always just use the software, play around with it to verify if the diagrams are correct or not. And if you have any questions, obviously you can always just let me know. And then yeah, so I'd like to conclude this part of shear force or shear force and bending moment chapter 6. I wish you success for this preparation. At least you have some kind of guide on how the diagrams will look like, but you have to practice. I mean, I will have so much time to get you up to speed. So let's take what is our in 1320, right? If I'm correct. 1320, if I'm correct. So let's take a 30-minute break, a bit of a long one, just to refresh our minds, and then we can start on trusses. And then yeah, we might have a small break because that's going to be around 2 hours 20. Is it 2 hours? No, that's going to be 1 hour. Yeah, 2 hours 20 minutes. Yeah, we can have a small break in between. Hopefully I should be able to cover everything. Okay, let's see at 11, and then just make sure you arrive just before 11. Obviously it's 25 past now, like 5 to 11, and then we can continue with trusses. Okay, cheers.